Hi everybody. In this video we're going to look at evaluating the surface area for solids of revolution. If you remember, in previous lectures we discussed methods of evaluating the volume for solids of revolution. Those involve the disk, washer, and shell methods. Well, now we want to take a look at finding the surface area. So to start, let's assume that we're given a function y equals f of x, which is continuous, non-negative, and has a continuous first derivative on the interval from a to b. So down here we have the graph of such a function right here for x varying from a to b. And what we're going to do is we're going to rotate this around the x-axis. So if we rotate it around the x-axis like that, then this curve will generate a surface, and that surface will look something like this. So here's the surface that would be generated by rotating that curve around the x-axis. Notice that the x-axis is right here. So the x-axis runs through the solid in that manner. And our curve is right here. So right there's the curve. Rotate that around the x-axis and you generate this surface. Now we want to calculate the surface area for this surface. So the way we're going to do that is sort of similar to the way in which we calculated the arc length of a curve. So let's go back to the graph of the original function. Now here's the graph of the curve that we are rotating around the x-axis to form that surface. Now we want to calculate the surface area. So what we're going to do is this. We're going to take the interval from a to b and partition it into n subintervals, very much like what we did for calculating the arc length. So we're going to, let's say in this case, we're just going to partition it, say, into 4 subintervals. And then we're going to plot the corresponding points here on the graph. And now what we're going to do is just connect these dots with straight line segments. And now what we're going to do is we are going to rotate these straight line segments around the x-axis, and they're going to form and they're going to form sort of cut-off cone shapes. And we're going to be able to calculate the lateral surface area for each of those cones, sum them all up, take the limit as n goes to infinity, and we'll end up with an integral formula. So let's focus on one of these straight line segments right here. Let's take a look at this one right here. Now if we rotate this straight line segment around the x-axis, we'll get a shape that looks something like this. And so this is the shape that would be generated. So it looks like a cone that has the top of it cut off. We call this shape a frustum. Now what we want to do is calculate the lateral surface area of this frustum here. So lateral surface area, meaning the surface area as we go around like this. So we want to calculate that surface area. So to do that, let's label a few things on this frustum. First of all, let's note the radii of the two ends. So let's label them like this. Let's call this radius right here. That one right there we'll call R2, and this one over here, let's say, is R1. So let's label them as And let's also note the relationship between R1 and R2 and the function f of x. So notice that R1, that's equal to f of xi, right? That's the distance from here to here up to the curve. If we label this point right here as xi on the x-axis. So xi represents the left-hand endpoint of your ith subinterval. And then R2, let's label that as, so if we label this point right here as x sub I plus 1, that's the right-hand endpoint of your ith subinterval. Then R2 is this distance, which is f of x sub I plus 1. So we'll label this point right here xi, and that point right there xi plus 1. And so you see that's the relationship between the radii and the function f. And let's also label this distance, the length of that line segment right there, let's call that our delta L, like that. Now I claim that the lateral surface area of this frustum is then given by this. And I'm going to call that delta L. I'm going to label that as delta L sub I here, just to indicate that it comes from the ith subinterval. Now let's notice something about this formula to understand why this represents the lateral surface area of this frustum. Notice that this term right here is your average radius. And so if we multiply that by 2, then this term here is going to be our average diameter. So that's our average diameter between R1 and R2. And then if we multiply diameter times pi, that's going to give us our average circumference. So this term right here is just our average circumference. And now if we multiply that by this distance here, we get the surface area for the frustum. So it sort of makes sense that the surface area for this frustum is its average circumference times the length of that line segment. Now that's not a rigorous proof, of course, but it sort of makes sense where this formula comes from. So now let's clean this formula up a little bit and take note of how we can rewrite this delta Li term. So we can cancel the 2's, of course, and we end up with this. Let's replace R1 and R2 with f of x sub I, f of xi plus 1. Now the delta L term, let's take care of that. Let's notice that this delta L term well, notice if we form a triangle in here, let's call this distance delta x, and this distance right here we'll call delta y sub I. And so the delta L is going to be, of course that's just a Pythagorean theorem, factoring out a delta x squared like we did previously with the arc length derivation, we get something like this. So that's where we just factored out a delta x squared term from here and from here. And then we moved it outside the square root, so it just becomes a delta x. Now this term right here, as we discussed previously with arc length, that can be replaced by a f prime of, let's call it ci. So the CI is somewhere between xi and xi plus 1. So let's say that that's like right here. And once again, that comes from the mean value theorem, right? Remember, the mean value theorem states where the denominator here is your change in x, so that's the delta x, and the top is your change in f, or change in y. And so there's some c value between a and b where the derivative is equal to delta f over delta x. And that's exactly what we're saying right up here. So now we can write this delta L sub I as follows. So this is going to be, we multiply this by the square root of 1 plus and there we go, we have our full formula now. Now let's sum all of these delta SI's together and we'll get an approximation for the surface area, and we'll take the limit as n goes to infinity and we'll see that we get an integral coming out. So then the total lateral surface area S is going to be approximately the summation of all of these terms right here. Now this is just an approximation, but when we take the limit as n goes to infinity, then we get equality right here. So let's replace this with an equals, and then put a limit as n goes to infinity, and then we see now that this term right here will turn into our integral pi. We replace all the xi's with just x's. And so we see that what we're going to get here is 2 times f of x, because we're going to have 2 f of x's. Now the f prime of ci, well, what does the ci become? Well, the ci is nestled in between xi and xi plus 1. And as n goes to infinity, these two values are getting squeezed together to form a single x. So the ci must equal that x. So the ci also is just x. And the delta x, that just becomes a dx. And our limits of integration go from a to b. From a to b. And so now we have our formula for the lateral surface area of the surface generated by rotating this curve around the x-axis, and is given by this. And there we go, that's our formula. So it's 2 pi times the definite integral from a to b of f of x times the square root of 1 plus your derivative squared, and that will give you your lateral surface area. Now, there's one important thing to notice here. This f of x right here should be thought of as a radius of a thin frustum formed as we let n go to infinity, or delta x goes to 0. You notice as we let n go to infinity, these two lines right here are merging into one to form a single f. So this should be thought of as a radius of a very, very tiny frustum. And that's important because if we change the axis of rotation, this term is what you will have to adjust. If we change the axis of rotation, if we move it up or down, you will have to change this term. This term will not need to be changed, only this term. And we'll see that when we take a look at a few examples. Now let's take a look at a summary of our result. Now here's a statement of the theorem we just developed. Let f of x be a continuous non-negative function which has a continuous first derivative on the interval from a to b, and let's denote c equaling f of a and d equaling f of b. Then for x-axis rotation, the lateral surface area of the solid generated by revolving the curve y equals f of x about the x-axis is given by this formula, and this is what we have just developed. Now just note the lateral surface area means that you don't include the surface area of the ends, which oftentimes just form two circles. You're not including the surface area of the ends. And also it's important to note, as we mentioned previously, you should think of this f of x as being the radius of a very thin frustum. And this is what will have to be adjusted if you change your axis of rotation. If you move the x-axis of rotation up or down, you'll have to adjust this f of x term, as we'll see in upcoming examples. Now for y-axis rotation, you need to take the curve y equals f of x and solve for x in terms of y to write it as a function x equals g of y. Then if you rotate the curve around the y-axis, this is going to be the formula for your lateral surface area. So notice we take 2 pi multiplied by the integral from c to d. Recall c was f of a, d was f of b. And then it's the definite integral from c to d of g of y times the square root 1 plus. Now we have to take the derivative of g with respect to y and square it. And all of this is underneath the square root. And so this is our formula for rotation around the y-axis. And once again, this g right here should be thought of as the radius of a small frustum that's oriented perpendicular to the y-axis now. And this is what will need to be adjusted if you move the y-axis of rotation left or right. Now let's take a look at a few examples. Now for this example, we start with the curve y equals x cubed for x between 1 and 2, and we want to find the lateral surface area when that curve is revolved about these different axes of rotation. So the first one we want to look at is the x-axis. Now here's what the graph of our function looks like. This is the graph of y equals x cubed right here for x between 1 and 2. Now when you rotate this around the x-axis, it generates a surface that looks like this down here. So this is the surface that would be generated. Right here would be the x-axis running this way. So this would be the x-axis, and our curve would be right about here. That's our curve y equals x cubed. And this is the surface that we want to find the area of. So for rotation around the x-axis, recall that we want to use this formula right here. Now previously we may have written this as the integral of f of x times the square root of 1 plus df dx squared, but of course y equals f of x, so it's the same formula. Now in this case, the y equals x cubed, the a is 1 and the b is 2. So we just have to plug this information into our formula and evaluate it. So right here we plugged x cubed in for y, and right here is our derivative 3x squared. That's the dy dx term. And so just simplifying this a little bit, 3x squared squared is going to be 9x to the 4th. And so this is what we need to evaluate to get our surface area. Now we could do a substitution here. We could let u equal, in which case then the du . And we see that the x cubed dx would become du divided by 36, and the square root of 1 plus 9x to the fourth would become u to the 1/2 power, or the square root of u. Now, to evaluate the antiderivative here, we can just do this in our head since we know this substitution will work. So we could just do it like this. If we add 1 to 1/2, we of course get 3/2. So we know that the antiderivative of this is going to be some multiple of 1 plus 9x to the fourth to the 3/2 power. However, if we were to differentiate this, we would drop the 3/2 down, but we don't want a 3/2. So we would have to multiply this by 2/3. Then we would subtract 1 from the exponent, and that would give us the square root. But then we would need to multiply by the derivative of the inside, which would be 36x cubed. That's what we would get when we would differentiate this. So that would give us our x cubed, but it would also give us a 36. We don't want a 36, so we also have to multiply this by 1 over 36. And then we also have our 2 pi out front. And so this is what our antiderivative would be. And simplifying all of this right here, we get pi over 27. And so that's what we have right here. There's our pi over 27 times 1 plus 9x to the fourth to the 3/2 power. And now we just have to evaluate that from 1 to 2. Plugging 2 in here for x, we get this. And plugging 1 in here for x, we get 10 to the 3/2. And so this is our answer right here, which we can write as pi over 27 times 145 to the 3/2 power minus 10 to the 3/2 power. And you could simplify that on a calculator or come up with a decimal approximation if you like. And that would be our lateral surface area if we rotated the curve y equals x cubed about the x-axis. Now let's take a look at part B. Now for part B, we want to rotate the curve y equals x cubed about the line y equals -1 to generate a surface, and we want to find the surface area for that surface. So notice that the line y equals -1, we have it labeled over here in our graph. Notice that it is parallel to the x-axis. So what we want to do is we want to take the surface area equation for rotation around the x-axis and modify the y of x term. That represents the radius of small frustums. So what we're going to modify it to is y plus 1. And to see why, let's go over to our graph over here, and what we would want to do is draw a thin frustum from the curve down to your axis of rotation like this. So think of that as being a thin frustum. Now you could add some thickness to it if you like to, recognize that it's a frustum, and remember the frustum is really measuring the surface area of that black little line segments as it's wrapped around the axis of rotation. Now the y of x term over here is supposed to measure the radius of this frustum right here. Now if we move the axis of rotation, if we shift it down, you see the radius, we have to take y and add 1 to it. In other words, if you think of a point right here, say that point right there is x comma y, then the radius of this frustum is going to be this distance. Well, that's going to be this distance, which is y, plus this distance, which is 1. You see this distance here is y, and this distance is 1. So the radius of this frustum is y plus 1. So all we have to do is change this y to a y plus 1, and that's all we have to do. The dy dx here does not change. That stays dy dx here. And our limits of integration do not change, because you see the x here in this equation, x is like sitting right here. That still varies from 1 to 2. That doesn't change just by shifting the axis of rotation down. So our limits of integration are still 1 to 2. And then we can evaluate everything here. So we replace the y with x cubed plus 1, and then we have our square root 1 plus, and the 9x to the fourth comes from the fact that dy dx, this term right here, is 3x squared. And there's our answer right here. And so if we were to evaluate this integral, that would give us the surface area for the surface generated by rotating this curve around the line y equals -1. Now this integral right now, we're not in a position to be able to evaluate it, by hand anyway. Notice if we distributed the square root, multiplied it by x cubed, that portion we could integrate via substitution. But then when we multiply it by 1, we get an integral from 1 to 2 of the square root of 1 plus 9x to the fourth. We're not in a position to find an antiderivative for that term yet. We'll be able to do it later on, but as of right now, we need some other integration techniques that we haven't covered yet. Now for part C, we want to rotate the curve y equals x cubed about the y-axis to generate a surface, and we want to find the surface area. So we need to start with our equation for surface area if we rotate around the y-axis, and that's given by this formula right here. Now don't get confused. Previously we had written g of y right here in place of this x of y and dg dy. Well, we're just letting x equal g of y here. And there's a reason why we do that. You'll see when we start labeling things over here. Now to find x of y, what we want to do is take our equation, y equals x cubed, and solve for x in terms of y. So solving this for x in terms of y, we just take the cube root of both sides, or raise both sides to the 1/3 power, and we get and so the function x of y equals y to the 1/3, or g of y equals y to the 1/3. Now we need to take the derivative of that and plug it right in here. So notice the derivative of y to the 1/3 is 1/3 y to the -2/3 power when we differentiate this with respect to y. And now we just need to plug everything in this formula up here. So x is y to the 1/3, dx dy is 1/3 y to the -2/3, and notice that our limits of integration now are 1 to 8. And that comes from our graph over here. Notice when x is equal to 1, y is equal to 1, and when x is 2, y is equal to 8. So if x varies from 1 to 2, then y varies from 1 to 8. And we need that because you see we're integrating with respect to y, so we think of y as varying from 1 to 8. And then 1/3 y to the -2/3 squared, that just simplifies as 1 over 9 times y to the 4/3 power. And this is the integral that we would have to evaluate to find the surface area. Now we're not in a position to evaluate this yet, but we could use approximation techniques like Simpson's rule to approximate this definite integral. Now for part D, we want to rotate the curve around the line x equals 3. So what we need to do is take the formula up here for rotation around the y-axis and modify the radius term right here. Notice that our line over here, x equals 3, is parallel to the y-axis, so that's why we use this formula up here, and we just need to modify the radius term. Now this is where it comes in handy to draw a little frustum. So what we want to do is draw a small thin frustum from your curve to the axis of rotation like this. So that represents a thin frustum. You could put a little thickness to it like that if you want. So here's our frustum, and we need to calculate the radius of it. Well, let's label a point like right here. Let's call that x comma y. Now we want to calculate this distance right here. Well, that distance is going to be 3 minus x. You notice this distance here is 3, and the distance from here to here, that distance is x. You see it's coming from the coordinate x comma y. So this distance here is going to be 3 minus x. And that's going to be our radius term. So instead of x, we're going to replace it with 3 minus x, and that's exactly what we do. So down here we have our modified formula. So our surface area, 2 pi, and we're going to integrate from c to d, 3 minus x. That's exactly what we have right here. And the x is still y to the 1/3 power. That doesn't change. dx dy is still 1/3 y to the negative 2/3. And our limits of integration are 1 to 8. You can see right here, think of the y as sitting right here. The y varies from 1 up to 8, and that comes from our original equation, remember? And we had restrictions on this with x going from 1 to 2. So if x is 1, y is 1, and if x is 2, y is 8. So y goes from 1 to 8. And right here is our integral that we could evaluate. So you notice that it's similar to the integral that we had before for rotation around the y-axis, but we had to modify the radius term, y to the 1/3, to 3 minus y to the 1/3. And let's take a look at another example. Now in this example, we want to verify that the surface area for a sphere of radius r is 4 pi r squared. That's the surface area. If you recall, the volume of a sphere of radius r is 4/3 pi r cubed. Well, we want to verify that the surface area is 4 pi r squared. So to do that, what we're going to do is take a curve representing a circle of radius r and rotate it around the x-axis, like this. Now this curve, recall that for a circle of radius r, its equation is given by so that's a full circle of radius r. So if we only want the upper half as we have drawn here, then we would solve this for y, and we would get so that's the equation for this curve that we have drawn here. Now what we're going to do is rotate this around the x-axis and apply our surface area formula for rotation around the x-axis and verify that we get back 4 pi r squared. Now for this circle here, let's notice that the endpoints right here are at negative r and r. Now if we're going to do rotation around the x-axis, we want to apply this formula that we have down here. Recall for surface area of a curve rotated around the x-axis, this is our surface area formula. And so now all we have to do is plug all of our information up here in our picture into this formula. So the y is going to be the square root r squared minus x squared. We need to take the derivative also, so let's note that the derivative here, so if we differentiate this, we have to think of this as being, and when we differentiate this, drop the 1/2 down, subtract 1, we're going to get And so recall the negative 2x came from taking the derivative of the inside term right here. That's by the chain rule. And all of this simplifies to and there we go. So there's our derivative, negative x over the square root of r squared minus x squared. And now we just have to plug everything in this formula. Now the a and b, they're going to be negative r and r, or we could integrate from 0 to r and multiply this by 2, taking advantage of symmetry. So applying this formula then, we get that our surface area So there we go. Notice that we replaced the y with square root r squared minus x squared, because recall we have to integrate with respect to x here. So we need everything in terms of x, so we wrote what the y is in terms of x. So right there it is. We have to square the derivative right here. And when we square this term, we get x squared over r squared minus x squared. Notice how the square root went away because we're squaring it. And so we have to simplify this right here and evaluate it. Also notice we went from 0 to r instead of negative r to r, and so we then had to multiply by 2. So we're taking advantage of symmetry. It'll make it a little bit easier to evaluate this by going from 0 to r instead of negative r to r. So let's simplify this now. So to simplify this, we're going to find a common denominator here to simplify the 1 plus x squared over r squared minus x squared term, or just cross multiply if you want to think of this as 1 over 1. And what we would get is the following. And so there we go, that's what we get. Notice that the r squared over r squared minus x squared term came from cross multiplying the term underneath the square root up here, or finding a common denominator, replacing 1 and 1 with r squared minus x squared over r squared minus x squared. And now simplifying this, notice if we break up this square root here as the square root of r squared divided by the square root of r squared minus x squared, that these terms will cancel. So this square root here will cancel with everything under here. And what we'll end up with then is the following. And of course the square root of r squared is just r. Now be careful when we integrate this. We're integrating with respect to x, so we treat the r like a constant. So the antiderivative of r is going to be r times x, right? R is like a constant, like the number 5. Antiderivative of 5 with respect to x is 5x. Right? Don't make the mistake of writing this as r squared over 2. We're not integrating with respect to r. And putting in an r in for the x here, and a 0 in for the x, and subtracting, we get and that's exactly what we wanted. So we've verified the surface area for a sphere of radius r to be 4 pi r squared. And let's take a look at one more example. Now for this example, we're going to take a sphere of radius 4 inches and drill a hole of radius 2 inches through the center of it. Then we want to find the total surface area of that solid. So to solve this problem, we're going to take a region, rotate it around an axis, in this case it's going to be the x-axis, to generate our solid. And then we're going to use our equations for surface area to find the total surface area. So here's the region that we're going to rotate around the x-axis. So you see, if we rotate this region around the x-axis, it will generate a sphere with a hole cored through the center of it. Now the equation that we want for a sphere of radius 4 is going to be, so that's a circle of radius 4 that forms an entire circle going all the way around. Now if we only want the upper portion of the circle here, then we're going to solve this for y in terms of x, and we get, so that's the equation for the upper part of the circle here. Now this piece right here is going to be the line y equals 2. So that'll form our hole of radius 2 being drilled through the center of it. So now we have two pieces to find the surface area of. We have this curve and this curve. Now the dotted line here is going to be easy. That's just going to form a cylinder. It's easy to find the surface area for a cylinder. We don't actually have to use the surface area equation that we had before. We can just use a little geometry. Now for this curve up here, we're going to be rotating around the x-axis. And so we want to use our surface area formula for rotation around the x-axis. So once again, we're going to use this one where we're integrating with respect to x. And the y of x here we think of as being the radius of a small frustum. Now the y is going to be given by this equation up here, and we have to determine our limits of integration a and b. Now for this portion of the curve right here, let's determine our limits of integration a and b. Now this is supposed to be a hole of radius 2 being drilled through the center of our sphere. So what we have then is we can use a little bit of right angle trigonometry here to determine our limits of integration like this. So this distance is 2. I know the radius of my circle that I'm rotating around the x-axis to generate my solid is 4. And so then the distance here, that point right there, is just going to be the square root of 4 squared minus 2 squared. And so that's just going to be the square root of 12, or 2 root 3. So that's the point right there that we're going to be integrating to. So that'll be our upper limit of integration right here. Now we can take advantage of symmetry. We can let the a be 0 and then multiply this by 2 for this half over here. So then our lateral surface area, the surface area for just this portion of the curve being rotated around the x-axis, is going to be as follows. Now we have to take the derivative of this with respect to x, put it in here, and square it. Also notice that I replaced the y with the square root of 16 minus x squared. Now the derivative of this, that's going to be and I'll let you verify that. That's just using the chain rule and rewriting this, the y, as 16 minus x squared to the 1/2 power, and then differentiating, you get this. So now we square this and put it in here, and we get now this will simplify as Now, we obtained the 16 over 16 minus x squared just by simplifying what's underneath the square root here. Once again, you could cross multiply to get this, or find a common denominator here. Rewrite the 1 as 16 minus x squared divided by 16 minus x squared, and you'll get this. Now notice, if we were to break up the square root of this fraction as the square root of 16 divided by the square root of 16 minus x squared, notice how these terms will cancel. And then what we're left with is the square root of 16, which of course is 4. So we just moved the 4 outside, multiplied it against the 4 pi, and then we get and then of course this is just going to be 16 pi times 2 root 3. We get that from just putting 2 root 3 in for x, 0 in for x, and subtracting. And so we're getting here, and there we go. So that will be the surface area of this portion of the curve rotated around the x-axis. Now we have to find the surface area of the inside, and that's just going to be a cylinder. And let me just draw a three-dimensional representation here to convince you it's a cylinder and to find its dimensions. So you notice when we rotate this region around the x-axis, we generate the solid as I have pictured here. So now we need to find the surface area of the cylinder here that's inside the sphere. Well, to find the surface area of the cylinder, let's note that the diameter of the cylinder is 4. That diameter is 4 because the radius is 2. And previously we have found that this point right here is 2 root 3. And so the length of the cylinder is 4 root 3. This distance is 4 root 3. So therefore the surface area of the cylinder is going to be the circumference of the circle here, which is going to be pi times 4 times the length. And so therefore the surface area of the cylinder is going to be 4 pi times diameter, that gives us the circumference of the circle, times the length of the cylinder. And so we're getting back, so this is the surface area of the inner cylinder, this is the surface area of the outer portion of the sphere, and so we just add them together and get our total surface area. And there's our answer, 48 root 3 pi, and that came from adding these two numbers together. And that concludes our lesson on surface area.